about to start the third session, session 3. And the special aspect of this session is that it's the least digested topic in the sense that there was no study, no group study of this topic. The story actually starts 100 years ago when Einstein wrote down his equations for the theory of gravity that he called the general theory of relativity. That was 1915. He published the last version of these equations in November, at the end of November, November 26, 1915. And then shortly afterwards, he derived some interesting effects of the general theory of relativity, one of which later on had to do with the deflection of light. And in 1919, a group of astronomers led by Arthur Eddington went to test this prediction of the deflection of light by the sun, and they claimed agreement, even though the data points had huge error bars, and in retrospect they were not justified in making this statement. However, the statement was correct. And that was the first important verification of Einstein's theory of general relativity. And since then, we had many more confirmations of this theory, the latest of which was exactly 100 years later by the LIGO experiment. And that was a great triumph of the same theory in the sense that it was tested at the strongest possible regime, which is near a black hole, where space-time is distorted so much that even light cannot escape from the inside of the horizon of a black hole. And yet, two such black holes that collide produce very strong ripples in space-time that could not have been calculated precisely until 10 years ago. And computer simulations predicted the expected signal, and it agreed perfectly with the observed signal 2 days after advanced LIGO started looking at the sky. And so altogether, this theory of general relativity is well confirmed, and also black holes we know now definitely exist. And therefore, it appears as a rather straightforward result that the sun could act as a gravitational lens. And the fact that light is deflected by the sun, it's deflected by a very small amount when we observe it from Earth, but if we move far from the sun, the light will be focused at some focal point, and it's easy to calculate where that would be. It's at a distance of at least 550 astronomical units. So if you go to a distance of 550 astronomical units, the light from a distant source will be focused. And of course, you can go to larger distances and you still will find focused light there. And so the issue is, can we build an observatory at the focal point of the sun, and would that be of interest? So there are two aspects to it. One, transporting the instrumentation to that location. That's a very challenging task. But more importantly is whether it's worth it. I mean, what will we do with it? And what are the obstacles? Obviously, you have a very bright star at the middle of your lens. That's not the best construction for a telescope. You want to block that sun and be able to remove the sunlight and the scattering by the corona of the sun to a very high precision such that you can detect these images, the lensed images of the background source. And then there is an interesting general question: what would you like to look at? I mean, obviously, this is a gigantic telescope, much bigger than anything we can construct. And so there are opportunities to image a planet, to image a black hole, to do all kinds of things. So what we'll discuss in this session is these lists of possible issues that come with using the sun as a gravitational lens. And I should say that any of the speakers and also the panel did not study the subject in great detail at the same level as the previous sessions we had. And so this is more of a brainstorming session. We'll start actually with one of the people that worked on this subject, wrote a paper about this subject, Slava Turishev, and he will talk about direct multiplex imaging of an exo-Earth with a solar gravitational lens mission. Slava.